So here we've got an object of 10 kilograms that starts off as just one big object, but then it explodes into three pieces. So if we take a look at initial and final situations here, initial is just this one large object, 10 kilograms. And it says it's at rest. So what should we expect about its initial velocity?
Could be 0.
Yeah, initial velocity is 0. So it starts off not moving at all. But then it explodes and it turns into three pieces. And it tells us piece 1 is 3 kilograms. And piece 2 is also 3 kilograms. So what would piece 3 have to be?
One kilogram?
They need to add up to 10 kilograms though.
Oh, 4.
Yeah. So we know the masses of all three pieces, and we know the final behavior, the final velocity of piece 1 and piece 2, just not piece 3. So let me label those as well. It tells us piece 1 goes due west at 10 meters per second. And piece 2 goes 45 degrees north of east at 5 meters per second. And we don't know the final velocity of piece 3. That's what we're trying to figure out. Any questions on that setup so far? So the idea of conservation of momentum is if we take a look at the momentum before the explosion and the total momentum of the whole system after the explosion, what should we expect about the initial total momentum and the final total momentum? Or first of all, what is meant by momentum in the first place? How is momentum defined? What is momentum? Change in velocity would be acceleration. Acceleration describes how quickly the velocity is changing. But momentum isn't about change in velocity. Momentum is just the velocity multiplied by the mass of the object. So velocity is how fast the object is moving, including which direction it's traveling. Velocity is a vector, so it counts as having direction. If you take that velocity and multiply by the mass of the object, that tells you the momentum of the object. So momentum is a description of the object's motion, including how fast it's going and in which direction and how massive the object is. Those all contribute to the momentum. So for example, if we take a look at the before situation, before we've got a 10 kilogram object moving at velocity 0 meters per second. So what would its momentum be? Yeah, its momentum would be 0. So we can say at the beginning, the system has 0 momentum. And in the final situation, we should expect that momentum doesn't change, because what's the only way you can change the momentum of an object? If you got an object with some amount of momentum, even if it's 0, how do you change the momentum of an object? You can't really change the mass of an object. We're assuming an object stays the same mass. Like in this case, we are changing from a 10 kilogram object to 3 kilogram, 3 kilogram, and 4 kilogram objects. But the mass didn't really disappear. If you just think of this original 10 kilogram object as already categorized into 3 pieces, a 3 kilogram piece, a 3 kilogram piece, and a 4 kilogram piece. Those pieces are already there. They just haven't separated yet. So let's treat it as if the object is already a already three objects, a 3 kilogram piece, a 3 kilogram piece, and a 4 kilogram piece that all just happen to be stuck together and not moving yet. So the mass isn't changing. But what is changing? From initial to final, what's changing? Direction, sort of. The thing is, it wasn't really moving in any particular direction at the beginning. But we're going from not moving at all to moving. So the velocities of the objects have changed. The 3 kilogram object changed from at rest to moving 10 meters per second to the west. The 3 kilogram object here changed from not moving to moving 5 meters per second to the northeast. And the 4 kilogram object changed from not moving to moving at some unknown speed in some unknown direction. But how do you make that happen? If you just got an object that's moving at some velocity, how do you change its velocity? What do you have to do to it to make that happen? Because if you don't do anything, it's just going to keep moving at that same velocity. Yeah, you've got to apply a force to it. If you got an object moving in some certain velocity, including possibly zero velocity, if you want to change that, you have to apply a force. There is no way to change velocity other than applying a force. So there's got to be some sort of force involved in order to change the momentum of an object. Because the momentum will only change if the velocity changes, and that requires a force to happen. So if you have one object, changing the momentum of that object requires a force to be applied. In this case, we've got several objects that are presumably applying forces to each other during the explosion. Like piece 1, piece 2, and piece 3 are all pushing off of each other. So there are forces involved internally to the system. Pieces 1, 2, and 3 are exerting forces on each other. So they individually change their momentum, but there's no forces from anywhere else. There's no forces on the system from outside the system. So we can expect that the total momentum should stay the same. So that's an important concept overall, that if there's a system of several objects you're considering, or possibly just one object, in general, the total momentum of a system of possibly several objects is changed only by an external force. External in the sense of coming from or interacting with something outside of the system of objects we're considering. So these objects are applying forces to each other, but that's all internal forces. The total momentum of the system can only be changed by an external force from something else. And since we're assuming this is just floating out in space somewhere far away from any other objects, I think we can assume there's no other forces acting on it. In particular, the change in total momentum is always going to equal the force, the external force times how much time the force lasts. External force, or possibly the sum of several external forces, times the amount of time the force lasts, tells you how much the total momentum changes. And this idea of force times time is generally called impulse. So impulse means some force being applied multiplied by how much time the force lasts. And that tells you how much the total momentum changes. Any questions on the terminology there so far? And in this case, what's the external force acting on this system? How much external force? Is there any external force acting on this object? None at all, yeah. And we can assume that because it says it's out in space, that there's presumably nothing else, or it doesn't say anything about anything else interacting with these objects. So I think we can assume that this is a closed system in the sense that there's no external forces acting on it, nothing else interacting with it. So that means if the external force is 0, if there's no external force, or if there are external forces but they add up to 0, they all cancel out, then total momentum does not change. Which means that the initial total momentum, the sum of all of the initial momentums, equals the sum of all of the final momentums. Any questions on that so far? And what's the initial total momentum of the entire system before the explosion? Before the explosion happens, what's the momentum of the entire object? Yeah, total momentum is 0 because nothing's moving. And since there's no external force, that means in the final situation, the total momentum also has to be 0. That doesn't mean nothing's moving. Individual pieces are moving, but their total momentum, the sum of all the momenta of the individual objects, have to add up to 0. So the total final momentum here should be 0 because the total initial momentum was already 0. In general, with no external force, the initial total momentum should equal the final total momentum. And we can write that as an equation, but it's also often useful to write it out in an organized chart like this. This idea of a momentum chart is you make a column for initial momentum, change in momentum, and final momentum, and then a row for each object in the system. In this case, piece 1, piece 2, piece 3, and also always a row for total. And then we can start filling in what we know. To begin with, since this is a closed system, no external force, we already know that the change in total momentum has to be 0. Strictly speaking, we should call that the 0 vector because all of these momentum quantities are vectors. They have direction associated with them. So the 0 here is not just the number 0, it's a vector called the 0 vector, a 0 with an arrow over it, which means a vector whose magnitude is 0. Also, we know that the initial total momentum happens to be 0, so the final total momentum also happens to be 0. So at the beginning, nothing's moving, so the initial total momentum is 0. In fact, we could even fill in the individual pieces. Piece 1 is not moving, piece 2 is not moving, piece 3 is not moving. So those all have 0 momentum. And again, those are all vectors, so strictly speaking, these should have vector symbols over them. It's not just the number 0, it is the 0 vector. And then with no change, the final total has to be the same as the initial total. Any questions on that so far? So we filled in all of the initial information that nothing is moving. We filled in the fact that the total change has to be 0 because there's no external force causing a change. So the final total has to be the same as the initial total momentum. We can now also fill in some of the final values because we at least have final values for the behavior of piece 1 and piece 2. Piece 1, for instance, what's the final momentum of piece 1, according to the information shown here? 30. Specifically 30, and what are the units on that? Well, it was 10 meters per second, but we're multiplying it by 3 what? Yeah, 3 kilograms. So we get 30 kilogram meters per second. However, since everything in this entire chart is going to be in kilogram meters per second, I'm not going to bother writing that every time. I'm just going to put a little note in the corner saying that these are all in kilogram meters per second. So that's the general unit of measurement for momentum, kilograms meters times second, or kilograms times meters over seconds. And there's no abbreviation for that as far as I know. It's just written as kilogram meters per second. But yeah, piece one, initial was 0 because at the beginning it was not moving. It says it's at rest, and then it explodes into 3 pieces. So at the beginning, it's not moving, so the initial momentum is 0. Piece one at the end is moving to the west with 30 kilogram meters per second of momentum. So I'll put a 30. But since it's specifically to the west, we should really draw an arrow here as well. The final momentum is 30 to the west. So we'll draw an arrow in that direction and label it with the magnitude 30. So the direction is to the west, the magnitude is 30. And what about object number 2? What would be its final momentum? Yeah, 15. And that's specifically 15 to the northeast, to the direction of travel. Because the velocity is 5 meters per second to the northeast. And generally, if you take a vector and multiply it by a scalar, you're modifying the magnitude, but keeping the same direction. The exception would be if you're multiplying by a negative scalar, that would reverse the direction. But mass is always positive. So 15 kilogram meters per second to the northeast. And you should draw these approximately to scale. Like this vector should be half as big as this vector. And then piece 3, we don't know yet. Any questions on that so far? But what's the one thing we know? Piece 2, the velocity is 5 meters per second, but momentum is velocity times mass. So we're multiplying 5 meters per second times 3 kilograms. And that will give us 15 kilogram meters per second. And that's really what momentum is. Momentum is a description of its motion and its mass. And mass, I think, is best to think of it as a measure of how difficult it is to change the motion. Like the more massive an object is, the more effort it takes to speed it up or slow it down a certain amount, the more effort it takes to change the velocity. So momentum really is just a measure of its motion, that is velocity, multiplied by difficulty to change that motion, mass. And what do we know about the final momentum of piece 1, the final momentum of piece 2, and the final momentum of piece 3? What should those add up to? Yeah, we know they add up to the total final momentum, which happens to be 0. So we can write that as an equation. We could say final momentum 1 plus final momentum 2 plus final momentum 3 equals the 0 vector. However, these are vectors. We're adding vector plus vector plus vector equals the 0 vector. And what should we usually do to add vectors together? What's the best format for adding vectors? Anytime you're going to be doing any calculations with vectors, what format should they typically be in? Like, can we just add 30 plus 15?
We make sure they're in the same direction. If
If they
not,
are in the
it's
same
negative.
direction. Sorry, what was that?
Oh, sorry. Like, if it's in the opposite direction, it's negative, right?
Well, vectors don't really have positive or negative signs. They have
Oh, okay.
magnitude and they have direction. So the magnitude is 30 and the direction is to the west. The magnitude is 15 and the direction is to the northeast. The magnitude is always non-negative.
Oh, okay.
If the vectors were pointing in exactly the same direction, then we could just add their magnitudes. Like 30 to the north and 30 to 15 to 30 to the north and 15 to the north would be 45 to the north. But these are not in the same direction. They're on the, sort of this offset diagonal. So we can't just add 30 plus 15. What do we need to do instead? What's a different format we should write these in first? Yeah, anytime you're going to be doing calculations with vectors, especially adding or subtracting, you should write them as XY components. So we want to split each of these up into how far or how much is it in the east-west direction as the X component, and how much is it in the north-south direction as the Y component. So for instance, this 30, how much of that is in the X direction and how much of it is in the Y direction?
For 30, is it negative 30 for X and 0 for Y?
Right. To the west is the negative X direction in the coordinate system we're using. So we could write this as negative 30, comma, and then none at all to the north or south. So final momentum of object one can be written as negative 30, comma, 0, in the sense that that's the X component and Y component of this vector. And what about piece two? It looks like piece two has both an X component and a Y component. So how would we split that up into X component and Y component? How would we find those legs of the right triangle here?
Do we use like degrees, like sine, cosine?
Yeah, sine and cosine will work here, the trigonometric functions. Because in this triangle, this is a right triangle, so we can use right triangle trigonometry. We know the hypotenuse is 15, and we know the angle of elevation here is 45 degrees. So let's zoom in on that triangle here. We've got this 15 hypotenuse. And we've got unknown sides, X component and Y component.
How do we know it's 45 and not like 60 or 30?
Specifically tells us that the object is traveling 45 degrees.
Oh, okay.
Or alternatively, if it said like due northeast, that would be exactly 45 degrees. So if we know this is 45 degrees, and we know that the hypotenuse is 15 kilogram meters per second. Then how would we find, let me label these. Let's call these PX and PY. So what equation could you write out using trigonometric functions here? If we wanted to find, let's say, PX. What trigonometric function would relate to the PX to the 15 we already know? And the 45 degree angle.
Would it be like cosine 45 equals, yeah.
Yeah, cosine 45, because cosine is going to be the adjacent side over the hypotenuse. So that'll be cosine 45 degrees equals PX over 15. And then to solve for PX, we can just multiply both sides by 15. And cosine 45 degrees happens to be root 2 over 2. So we just get 15 times root 2 over 2, or 7.5 times root 2. Any questions on that so far? And then for the Y component, what would be the only thing we'd need to do differently? Since it's the opposite side, what would we use? Yeah, we'd use sine of 45 degrees. So Py, the y component, would be the same hypotenuse times sine of 45 degrees. However, since 45 degrees is exactly half of a right angle, it turns out that cosine and sine of 45 degrees are the same. So in this case, the y component will also be 7.5 times root 2. Any questions on that so far? And that works out to about 10.6, I believe. So that means the x and y components are both about 10.6. And since that's to the east, we'll call that positive. Since that's to the north, we'll call that y component positive as well. So that'll be 10.6, 10.6 kilogram meters per second. So that's both of the vectors we know, the 30 to the west and 15 to the northeast, written in xy components. Whereas for P's 3, we don't know yet. So let's just spell that P final 3x, P final 3y. And leave those as unknown components. But what do they have to add up to? Yeah, the 0 vector. And the 0 vector could be interpreted as a vector whose components are 0 and 0. So we now have equations that P3 or P1 final plus P2 final plus P3 final has to equal 0, 0, the total final momentum. And the great thing about components is once we've written them in components form, how can we deal with these equations? What's the whole point of splitting them up into x and y components in the first place? Like, what would we actually do here to solve for P final 3x and P final 3y? Well, specifically adding what up to equal 0? What equations would we actually set up here?
Do we like add the x's like -30 and 10?
Yeah, we
Then
can
the same with
combine,
y.
right, we can combine just the x components in one equation. And then separately in another equation, we can combine just the y components. The x and y components don't really interact with each other in a meaningful way. We can keep them completely separate. So if we write that out, if we take a look at just the x components, we can say -30 plus 10.6 plus P final 3x equals 0. And likewise, if we look at just the y components, we can say that 0 plus 10.6 plus P final 3y equals 0. And then we can solve each of those equations individually. For instance, for the x components, -30 plus 10.6 would be -19.4. So what does P final 3x have to be?
Positive 19.4.
Yeah. And likewise, in the other equation, if we solve for P final 3y, what do we get?
-10.6.
Yeah. And of course, those should also be considered to be in units of kilogram meters per second. Now that we have values for that, we can actually fill that in. We can say that P3's final momentum is positive 19.4, comma, negative 10.6. Because that's what's needed to make all three of these final momenta add up to 0, 0. We can even draw that based on ideally to scale with what we've already got. So if we have 19.4 to the east, that is the positive x direction, and then 10.6 to the south, the negative y direction. So that's going to look like from here to here. So that would be the final momentum of piece 3, drawn as a magnitude and direction. To actually find the magnitude and direction, though, is going to need some more trigonometry. Before we do, though, any other questions on finding the xy components of that result? So let's bring in a bit more trigonometry then. We have, again, I'm going to draw this a little bigger. We've got this arrow that we know to be 19.4 to the east and 10.6 to the south. Label that. I guess I should call that negative 10.6. And ideally, we'd like to convert the x and y components back into magnitude and direction. Typically, if you're going to be doing any further calculations, x and y components are the way to go. But if you want to interpret the meaning of the final result, convert it back into x and y, or converting it back into magnitude and direction is usually a good idea. For example, the magnitude here, the actual length of this vector, how would we find that hypotenuse? Yeah, x squared plus y squared, the whole idea of the Pythagorean theorem. That hypotenuse, that magnitude squared, should equal the x component squared plus the y component squared. And of course, the negative here doesn't matter because we're squaring it anyway. So square root of 19.4 squared plus 10.6 squared is about 22.1. And again, that'll be kilogram meters per second. So we now have the magnitude, how strong the final momentum is. And we also want to know the direction. Which way is it actually traveling? And we usually describe that as an angle also. So how would we find that missing angle? We call that, yeah, tangent, inverse tangent should work. If we call this angle, let's say theta, tangent of theta would be opposite over adjacent. So tangent of theta is going to equal, in this case, what over what? What would be the opposite side and what would be the adjacent side here? Yeah, opposite is the negative 10.6, adjacent is the 19.4. So negative 10.6 over 19.4. And those are both measured in kilograms times meters over seconds, but since we're dividing, the units cancel out anyway. So this should be unitless. And then to find theta, you would take the inverse tangent or arctangent of that ratio. So negative 10.6 over 19.4. And I'm getting what is that? About 28.6 degrees, I think. Anyone want to try verifying that on a calculator? Or actually, I guess we should say negative 28.6 degrees because it's below the axis. But we could just describe that as 28.6 degrees south of east. So we say the final momentum is 22.1 kilogram meters per second. And the direction of travel is about 28.6 degrees south of east. Any questions on that so far? And a few other things we can do here. First of all, we want to figure out, ideally, we want to figure out things like how fast is the piece number 2 actually going? We have its final momentum, 22.1 kilogram meters per second in this direction, 28.6 degrees south of east. How would we convert that 22.1 kilogram meters per second into an actual speed to know how fast it's traveling? If we know the momentum, how do we convert that back to velocity? Yeah, momentum is mass times velocity. So to convert momentum back to velocity, we just have to divide by mass. Momentum equals mass times velocity. So therefore, velocity is going to be momentum divided by mass. So we take the 22.1 kilogram meters per second and divide by the mass, which is 4 kilograms. And that'll be 5.5, a little more than 5.5. And then kilograms cancel out, so we just get meters per second. So the final speed of the object, or the final velocity, I should say, because direction matters. Velocity is a vector. Final velocity of object 3 is 5.5 meters per second, and a direction of travel 28.6 degrees south of east. Any questions on that? And then from there, we could also even fill in the rest of the momentum chart. You might want to just stop here. If all you're looking for is what's the final speed and direction of travel of the object, we now have that. 5.5 meters per second in a direction of 28.6 degrees south of east. But you can also get some more information by filling in the rest of the momentum chart, specifically the change in momentum column. And how would you calculate delta momentum, or delta anything really? Yeah, final minus initial. And since the initials here are 0, final minus initial would just be final minus 0. So the changes would be negative 30, 0, minus 0, 0. And then 10.6 comma 10.6 minus 0, 0. And 19.4 comma negative 10.6 minus 0, 0. And filling in that change in momentum column, though usually not necessary, can still be useful for a couple of things. First of all, you can try adding up those changes and make sure they do add up to 0 as they're supposed to, because the changes should always add up to 0 if it's a closed system. And also the change in momentum can give you information about the forces involved. Because going back to the idea of impulse, that change in momentum equals force times time. For each individual object, we know the change in momentum. If you also know how much time the interaction takes, like in this case, how much time the explosion took, or if you got objects colliding, how much time the collision took, you can solve for force by dividing both sides by time. So change in momentum of that object divided by how much time the explosion or collision took tells you how much force that object experienced during the explosion or collision. Any other questions on that? All right, then I will see you next time.